Hello. In this video, I'm going to talk about vectors in R2, which we think of as the XY plane. We can also talk about vectors in just real numbers, or in R3, which would be three-dimensional space or four-dimensional space, or really any dimensional space. But for the purposes of this video, so that we can actually visualize what's happening, we're going to talk about vectors in R2. Most of the properties we're talking about here will carry over to other dimensional space. So let's say we have the vector 2, 5. Notice this is written as a 2x1 matrix. So our vectors we're going to think about as a column matrix where the number of columns is 1. So we think of these as column vectors. And we think about the 2 like the x-coordinate and the 5 like the y-coordinate. So here's our vector v. It has an initial point. When we're talking about putting vectors in the xy plane, we're going to use the origin as our initial point, and the point 2, 5 is our terminal point. So vectors have a direction. Think of it as directed line segment. It has an initial point and a terminal point. And we think of 2 and 5 as the components of the vector. So when I say component, it means these entries in the vector. So going back to v being the vector 2, 5, let's take another vector, negative 3, 0. Make sure that you can figure out what this vector looks like before I tell you. So I'm about to tell you. Okay, here is negative 3, 0. It's u. It has a direction, and it has an initial point of the origin and a terminal point, negative 3, 0. So let's say we wanted to compute the vector u plus the vector v. Algebraically, this works just like matrix addition. We're going to take our elements of v plus our elements of u, or vice versa, and add them together. So we add each component and we get negative 1, 5. Geometrically, we do what's called the tip-to-tail method. We're going to take our vector u and we're going to move its initial point to having an initial point that is the end of the vector v. So we're just shifting the vector u to the end of the vector v. And the result there is u plus v. Notice that the end of this black vector is negative 1, 5. Okay, so geometrically that's what this looks like. We're going to take u, we shift it to the end of v, and we get the result is u plus v. Now it didn't matter actually if I took u and put it at the end of v, or v and put it at the end of u. Because if I shift v instead to the end of u, I also end up with the same result. Okay, we get negative 1, 5. And geometrically, that's what vector addition looks like. Algebraically, it works exactly the same. Geometrically, this is what we're doing. Okay. Let's take these same two vectors, and let's say we wanted to compute, I probably did too much there. Let's say I wanted to compute 2 times v, a scalar multiple. This works in exactly the same way. I just multiply each component by 2, and I get 4, 10. Okay. If I wanted to think about what this was geometrically in terms of the vectors, I get a vector 2v. It's in the exact same direction as v was, only this time it is twice as long. So scalar multiples of vectors are vectors in the same or opposite direction with a scaled magnitude. Magnitude meaning how long it is. Okay, notice it's in the exact same direction, only just twice as long. Okay. So let's look at the same two vectors. And this time what I want to do is try to compute a linear combination of the vectors. Linear combinations of vectors are the exact same as linear combinations of matrices. It is a sum of scalar multiples of the vectors. Okay, I'm just going to add two scalar multiples of the vectors. So we know how to figure out what this is in terms of matrices. So that means that algebraically, what we're going to do is we're going to take 2 times the vector 2, 5 minus 1/2 times the vector negative 3, 0. I do the scalar multiplication first, and then I add them component-wise. So I end up with 5.510 as my new vector. Algebraically, I'm going to take the exact same 2 steps. So that means that I'm going to first look at 2v, and then I'm going to look at negative 1/2 u. Notice that when I multiplied negative 1/2 u, this time the vector went in the opposite direction, the exact opposite direction. That's what I meant in the previous sentence that I wrote that said scalar multiples are in the same or opposite direction. Notice that negative 1/2 u is in the opposite direction as u, and it has a different magnitude. It's half as long. So I computed each of those. That is like computing 410 and 1.50. You do both of those and then you add it using our tip to tail method. We get this vector here, which is, we can look at it by inspection, we get 5.510. So visually that's what's happening. Okay. So notice that this linear combination is not in the same direction as either of the vectors. We've created a new vector in an entirely different direction by taking a linear combination of the other two. Okay, so we're going to be talking a lot about linear combinations of vectors and what vectors we can get as linear combinations of the other two. So be looking for that. Also, these methods also are going to work with 3 dimensions. So you should be able to try to picture this in your mind, what's happening in 3 dimensions. It works 2 and further dimensions. I know it's harder to visualize what a 4-dimensional vector might look like. So make sure that you read in your book about all the properties of vector addition and scalar multiplication, thinking about what the 0 vector looks like and what all the properties are called.